Greetings to the audience. My name is Jay Nagle. I am a senior engineer in the Power Solutions Group at Semiconductor, located at the corporate headquarters in Phoenix, Arizona, focused on providing solutions in the automotive market segment. Here's the agenda for this session. We're going to start with an overview of Semiconductor, followed by our leadership in automotive semiconductors, some background on the electric vehicle market, an overview of 48-volt systems topology, and what competitive solutions Semiconductor provides in its automotive portfolio for this market segment. Automotive is one of onsemi's largest markets and focus of strategic growth. As you can see, global semiconductor sales are expected to grow from $36 billion in 2020 to around $68 billion in 2025. While we offer products used in all electronic subsystems within the vehicle, vehicle electrification and vehicle automation are where we see the greatest growth potential for the market and onsemi. If we first look at vehicle automation, onsemi is the market leader in image sensing for advanced driver's assistance systems and automated driving. With recent LiDAR and radar technology acquisitions and advancements in power supplies designed for automotive sensors, onsemi can offer a full suite of sensors needed to automate tomorrow's vehicles. Likewise, we can see that there will be a 10x increase in semiconductor content over today's internal combustion engines. onsemi's portfolio of IGBT and wide bandgap discretes and power modules are well positioned to capture a significant share of this market. Let's take a look at how onsemi's technology enables one approach to vehicle electrification: 48-volt mild hybrid systems. Let's take a look at the emerging electric vehicle market, its enablers, challenges, and benefits. Electric vehicle solutions encompass four main approaches: mild hybrid electric vehicles, which we'll focus on today, full hybrid electric vehicles, plug-in hybrid electric vehicles, and full electric vehicles, battery electric vehicles. This chart shows the forecasted growth over the next few years. Overall, electrification will grow by a compound annual growth rate of 24% between now and 2024, with mild hybrids and battery electric vehicles accounting for the largest growth segments. Likewise, traditional internal combustion engine vehicle volumes will decline globally by -3% during the same period. There are many factors driving this shift, including legislation designed to reduce greenhouse gas emissions and technological enhancements that are enabling a cost-effective transition to electric vehicles. The US, European Union, and Asia have put in place strict targets to reduce CO2 emissions from automobiles, in many cases targeting reductions of up to 50% by 2025. The demand for more fuel-efficient, cleaner transportation can be met by innovation in the semiconductor industry to develop smaller, higher efficiency, less costly power modules that are used to electrify the global car fleet. onsemi is a leader in this area, and we'll share some of those innovations with you. Electrification has its challenges. Batteries, which make up the bulk of the cost of an electric vehicle powertrain, still remain expensive, but innovation is quickly driving this cost down too. Also, what to do with the batteries at the end of the vehicle life remains an open topic. Do the materials get recycled? Is there a large enough secondary market for battery reuse? And so on. Battery electric vehicles have limited range, although it's improving. But how fast can batteries be recharged while on the road compared to the time to fill a gas tank? Are there enough fast charge stations available in the places people need to charge their vehicles? Electric motors, in particular, use magnets that contain rare earth materials. Efforts are underway to find alternate materials and technologies to mitigate the risks associated with rare earth materials. Broader availability of electric vehicles brings a range of benefits, including instantaneous torque, the ability to go to 0 to 60 in 3 seconds, a reduction in noise pollution, The total cost of ownership goes down, and most importantly, reductions in carbon dioxide emissions, cleaner air, and a positive impact on climate change. Before we discuss mild hybrid architectures in more detail, let's review the electric vehicle types available in the market today, their differences and contributions to creating that greener footprint. A microhybrid utilizes the standard internal combustion engine. Instead of using a standard alternator inherent in an internal combustion engine, it uses a belt-driven starter generator that is powered from the 12-volt battery. This modification enables the engine to stop running when the vehicle is not moving and the driver has their foot on the brake pedal. As soon as the pedal is released, the engine will restart. This eliminates engine idling, which translates into a 3 to 4% decrease in CO2 emissions. An evolution from the microhybrid is the hybrid and mild hybrid vehicle. The mild hybrid has an electric motor that supplements the internal combustion engine to implement start-stop, regenerative braking, vehicle coasting, and depending on the topology, propulsion at low speed conditions, contributing to a decrease in CO2 emissions by approximately 4 to 10%. In addition, these vehicles contain both the traditional 12-volt lead-acid battery and a 48-volt lithium-ion battery. The hybrid electric vehicle contains a larger battery ranging between 250 and 360 volts that supplements a smaller, optimized internal combustion engine capable of operating full electric mode for a short time span with assistance from the motor. This translates into a CO2 emissions reduction between 25 and 30%. Compared to full hybrid vehicles, the plug-in hybrid has much larger battery size, which enables operation for a longer distance range in full electric mode without assistance from the engine, but not completely. The battery will be recharged via regenerative braking and through the power grid. The longer range capability in full electric mode will contribute to a CO2 reduction between 50 and 100%. The battery electric vehicle utilizes an electric motor 100% for vehicle propulsion with zero emissions and 100% CO2 reduction for the entire range allotted by the battery charge. Overall, the trade-off between all vehicle types is CO2 emissions reductions coming with higher vehicle costs. The mild hybrid vehicle will be a popular choice because it creates the sweet spot for the consumer to achieve CO2 emissions and decreased fuel consumption at a reasonable cost. Compared to full hybrids, mild hybrids offer 50% of the CO2 reduction for approximately 30% of the cost of a full hybrid system. In taking a deeper dive into the 48-volt architecture, I will discuss the system-level blocks of 48-volt mild hybrid systems, how these components are integrated into the drivetrain, and the component solutions that Semiconductor offers to enable optimal performance in the vehicle. 48-volt systems will contain two voltage subsystems powered by a 12-volt lead-acid battery and a 48-volt lithium-ion battery. The typical drivetrain will contain the 12-volt starter and internal combustion engine. A starter generator motor will start up the engine, provide a boost in the torque force for acceleration, and charge the battery during regenerative braking. The starter generator motor is either integrated into the transmission or connected to the internal combustion engine using a belt. The starter generator motor is powered by the 48-volt battery using a three-phase inverter connected in line with the motor. With both 12-volt and 48-volt powered systems in the vehicle, a bidirectional converter is implemented to be able to transfer energy between both batteries. The 48-volt battery also drives loads that require higher power to operate, such as an electric supercharger, which is a device that forces air into the engine when a burst of power is needed for acceleration. Let's take a step back to answer the question of why there is 48 volts and 12 volts in a mild hybrid vehicle, and why 48 volts to begin with. The 12-volt battery functions to power devices that you would find in traditional internal combustion engine vehicles, such as interior electronics, body control modules, infotainment, and telematics systems. In order to develop fuel-efficient vehicles with performance features attractive to the consumer, heavy-duty pumps, compressors, turbos, and suspension components are integrated. These components require much more power to operate than what a 12-volt lead-acid battery can provide. In addition, the lead-acid battery cannot provide the acceleration boost that a higher voltage can. The 48-volt system is an optimal voltage source to support the drivetrains, since it's a generally safe voltage for humans to operate with, and a higher voltage can allow for a significant reduction in current and interconnect cabling to run the higher power systems. Less current means that smaller wiring can be used to reduce the size and weight of the vehicle wiring harnesses, which leads to the coveted CO2 emissions. Mild hybrid vehicle types and their level of capability are distinguished through their architecture. The P0 through P4 configurations represent the positioning of the electric motor with respect to the drivetrain. Depending on the configuration, different levels of functionalities are possible, yielding differences in overall system costs. Fuel efficiency and performance. The PO configuration represents an electric motor connected to the internal combustion engine using a belt and what is termed a BSG, which stands for belt starter generator. In a P1 configuration, the electric motor is connected directly to the crankshaft of the internal combustion engine and what is termed an ISG, which stands for integrated starter generator. The PO and P1 configurations are the most prevalent topology for mild hybrid vehicles today. In a PO configuration, the integration costs are minimal, but the resulting frictional losses due to the belt connection compromise the efficiency of the system. In a P1 configuration, you achieve a bit higher efficiency since you are not connected to a belt, which eliminates the frictional losses, and you can achieve higher torque for better boosting. In the P2 through P4 configuration, the electric motor is positioned where it is not connected to the drivetrain of the internal combustion engine, but integrated with the transmission as an integrated starter generator. This configuration yields the highest efficiencies, best recuperation, and even very low speed electric drive coming at an increased cost. The 48 to 12 volt converter is a multi-phase synchronous buck-boost bidirectional voltage converter. It functions as a buck converter to use the energy from the 48 volt battery to charge up the 12 volt battery, and also as a boost converter to use the energy from the 12 volt battery to charge up the 48 volt battery. A single phase is shown here for simplicity. The main blocks that constitute this converter are the source disconnect switch, buck boost half bridge, and current sensing stage, and the load disconnect switch. The source disconnect and load disconnect switch permit disconnection of the converter from the 48 and 12 volt battery using low RDS(on), high drain current MOSFETs controlled by gate drivers. High and low side gate drivers and 80 to 100 volt MOSFETs create a synchronous buck boost stage intended to minimize the switching and conduction losses and maximize the power efficiency of the system. The high and low side FETs in the buck boost stage control the direction of current flow between the batteries. A current sense amplifier is needed to monitor the inductor discharge current to regulate the battery charge. Since there are high currents running through these MOSFETs, the MOSFETs need to have low resistances and favorable thermal attributes. ON Semiconductor has a broad automotive portfolio of MOSFETs, amplifiers, and gate drivers in various configurations and packages to construct a system at the target efficiency. If the designer is seeking an integrated solution, ON Semiconductor has an automotive power module that contains an integrated solution for a three-phase bidirectional converter with 3 half-bridge circuits integrated into one package. The belt starter generator and integrated starter generator traction drive is very similar to the construction of an inverter for a battery electric, full hybrid, or plug-in hybrid vehicle that operates at a much lower voltage level. 80 and 100 volt MOSFETs are used to source the current from the 48 volt battery to apply a three-phase AC current to the electric motor windings. Gate drivers are used to create the PWM signals to switch the MOSFETs at the required frequency. Current sense amplifiers are available to monitor the current applied to the phase windings of the motors with a broad portfolio of components for signal processing and conditioning of sensor data. CAN transceivers for in-vehicle communication, a grade 0 EEPROM for parameter storage, small signal components such as digital transistors and switching diodes to support operation of the microcontroller, and ESD protection devices with fast transient clamping capability and low capacitances that protect the integrity of critical signals. Our flagship product, the 48 volt inverter system, will be our half-bridge 3 to 6 phase automotive power module to drive either a 3-phase or 6-phase electric motor. Compared to 3-phase motors, 6-phase motors can provide additional torque at the same power level. Each automotive power module consists of 2 high-side and 2 low-side devices mounted in parallel configurations. The power module is a highly integrated design with low thermal resistance and high current carrying capability, making it a high power density product. The device contains snubber circuits for improved EMI and enables lower stray inductance through its interconnect by being able to connect directly to the DC bus bar. One of the key advantages of this product is its transfer molded construction. Versus a gel-filled module, it has higher reliability, lower thermal resistance, and better warpage. Semiconductor provides a broad automotive portfolio to provide the complete solution for a 48 volt system. Semi provides the MOSFETs, automotive power modules, current sense amplifiers, power management devices, in-vehicle network communication devices, and supporting components such as EEPROM, ESD protection devices, and small signal discretes such as BJTs and diodes. To end the presentation, here are some models of our 25 kilowatt ISG reference design that, in addition to the automotive power module, populates ACQ 101 and 100 components from our automotive portfolio. This design was in full display in our booth at the CES Electronics Show this year in Las Vegas, Nevada. Thank you, everybody, for your attention.